Welcome to iLectureOnline, and now we're going to talk about the Big Bang in a chronological order, from the very beginning through the history of the universe to today. And so where do we start? Well, it turns out that from all the observations that we've made, we understand that the universe must have had a beginning. And all the observations that we made kind of point to the fact that there must have been a lot of energy at some point in time. The universe must have been very hot. All kinds of things must have happened to turn hydrogen into helium and to create the matter that exists today in the universe. So we're trying to make sense out of that. And we're trying to play the history of the universe backwards to the very, very beginning. So what must it have been like in the universe at the very, very beginning? And so when we started thinking about that, and of course I wasn't part of that, I'm just simply explaining something that some very, very smart people figured out on their own. But what they said was, everything in the universe seems to be quantized. For example, we know that energy is quantized. Energy, in the form of electromagnetic radiation, is quantized in small little chunks of energy called photons. And that is related to the frequency of those photons times a constant named Planck's constant. We also know that mass is quantized. For example, when you pour a glass of water, you're not pouring a continuous fluid into a glass. You're actually pouring chunks of water into the glass. The chunks are made up of molecules. And so we can say that mass is quantized. The number of molecules times the number of atoms times the mass of each atom, for example, or the number of molecules times the mass of each molecule. Things in nature tends to be quantized. So the question is time quantized? Is time a continuous fluid of thing, or is it actually something that is quantized into chunks of time? And so the assumption was that it was. The assumption that everything in the universe must be quantized in chunks of something. So what is the chunk of time? What is what we call the Planck time? Because we used Planck's constant to try and come up with what we thought was the smallest unit of time. And so they started throwing some constants together. They went to some very universal constants. For example, they used the universal constant of gravity because they figured that gravity was a big part of the existence of the universe. They used Planck's constant, which seems to quantify the Heisenberg uncertainty principle and seemed to quantify the quantity of energy that can exist, and also the speed of light, which is an absolute, the speed of which things like electromagnetic radiation can move through space. So they took those units and they started playing around with them until they ended up with something that was equal to time, equal to seconds. And so knowing that G is equal to 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared, and that H, Planck's constant, is 6.626 times 10 to the minus 34 joules times seconds, and remembering that a joule is a Newton meter, and knowing that the speed of light is 3 times 10 to the 8 meters per second, how do you combine those things to come up with something that is equal to time? And so they played around with it, and literally that's what they did. They do experiments with these kind of things. So they put all the numbers together. They came up with a very small number, 1.35 times 10 to the minus 43. And when they went ahead and put all the units together from those various constants, and I'm looking for my red pen, it's right here. And let's see what happens. So notice we have 2 kilograms in the numerator and a kilogram squared in the denominator. Notice we have meter to the fifth in the denominator, and have meters, meter squared, meter to meter. That's also meters to the fifth, so that cancels out. And we have seconds to the fifth in the numerator and seconds to the fourth in the denominator, so these cancel out 4 of those, and now we end up with second times seconds, and we take the square root of that, and sure enough, that is equal to seconds when we get rid of the rest of those. And so you can see here that this is then considered the smallest unit of time possible in the universe. So they said that the universe must have sprang into being at the time t equals 1.35 times 10 to the minus 43 seconds. And they call that time the Planck era, the very beginning of the universe, when the first unit of time clicked off the clock of the universe. So what was it like at that time? Well, they assumed that the temperature going back in time must have been 10 to the 32 Kelvin, an incredibly high temperature. And the time when the universe started was at 10 to the minus 43 seconds, based upon the assumption that that was the smallest time possible. Do we have any physics to describe that era? Not at all. There's nothing that we can do to describe what it must have been like in the universe. The assumption was that all the 4 forces that we understand today must have been unified into a single, what we call super force. That means the nuclear strong force, the electromagnetic force, the nuclear weak force, and gravity all were combined into a single unitary force existing in the universe. So, what happened then? Well, Time is a very strange thing. You have to keep in mind that yes, that was the first click of time, the universe started. We don't know what the universe was like, but it sprang into being. How big was it? It must have been extremely tiny, tinier than the smallest grain of sand on the beach of the earth. So, what was it like? It's hard to determine that, but you have to keep one thing in mind about time. Remember that the universe is very big. It's about 13.8 billion light years from Earth to the farthest regions in the universe that we can see. And we think the universe goes on beyond that. Matter of fact, we're fairly sure that it does. And so 13.8 billion years, or 13.8 billion light years away, meaning that any light coming from that region would take 13.8 billion years to reach us. And so from the other side, it would take another 13.8 billion years to reach us. So that's an enormously large universe that would take an enormous amount of time at the speed of light to traverse. It would take 27 point something billion years for light to traverse all the way across the visible universe. Now, that's for us. But what about light? How long would it take for light to cross the universe? It turns out that at the speed of light, time actually stands still. So if you were able to take a watch and put on a light beam as it travels across the universe, that clock, if it could move that fast, would not move at all. Time would simply stand still. And in perspective of the light would travel all the way across the universe in the blink of an eye, in an instant. So time is relative to from where you look at it. So who knows how time clicked forward in the beginning of the universe? We know that it must have started at time equals 0. What happened before that? We have no idea. What was the universe like at that point? We have no idea. But somehow time began to tick and the universe began to exist. And at that point, the universe went forward. So starting with Planck era, we're going to move through that event called the Big Bang, where the universe unfolded from what it was then into what it is now. So sit back, relax, and watch the next video and see what happens.